Magnetic field force on a moving electric charge. Not only do magnetic poles exert a force on each other, but a magnetic field will exert a force on a moving charge. If the charge is not moving, it does not feel a force. This is a very unique concept and phenomenon in the universe. The force on a moving charge is related to the magnitude of its charge, Q, its velocity, and the strength of the magnetic field, but only the portion of the magnetic field that is perpendicular to the charge's motion. This will become clearer in APC physics, but for now, here's the equation. F is equal to Q times V times B perpendicular. The previous slide gave you the magnitude of the force. Now we want to find the direction of the force. Basically, it's perpendicular to both the direction of the charge's velocity and the magnetic field. In vector analysis, this is called the cross product, or the curl. We're going to use the right-hand rule to find the direction of the force. Now, this is different from the right-hand grip rule that we showed earlier. That found the magnetic field direction to an electric current. This is a little bit different. Step 1. Point the four fingers of your right hand, make sure you use your right hand, in the direction of the charge's velocity. At this point, don't worry whether it's a positive or negative charge. That'll come after step 3. Step 2. Curl your four fingers, these guys here, perpendicular to your palm, and point them in the direction of the magnetic field. So we have the velocity of the charged particle it's moving, and we have the magnetic field in this direction. And finally, step 3. Extend your thumb perpendicular to your fingers. It is pointing now in the direction of the magnetic force on a moving positive charge. See how all these three vectors are perpendicular to each other. Charge was moving this way, field was coming in this direction, and the force is directed straight up. Now, what would be the direction of the force on a moving negative charge? I told you we would get to that. And what happens if the velocity of the charge is parallel or anti-parallel to the magnetic field? If the moving charge is negative, then the direction of the magnetic field force on the charge is opposite the direction of your thumb. So this is the direction of force on a positive charge. You would be down into the desk there if it were a negative charge. Also, if the velocity of the charge was either parallel or anti-parallel to the field, there is zero force. You can see that from the equation, which is Q times V times B perpendicular. So if it's parallel, there's no force. And frankly, you'd have a hard time having your fingers point in that direction and this direction at the same time. You just can't do it. And if the charge is not moving, then it also feels no magnetic field force. Let's look at the problem now without the hand. We have a negative charge moving this way and a positive charge moving this way with the velocity. The magnetic field, if you'll remember, the dots mean is coming out of the board. Use the right-hand rule to find the force on the positive charge. Then you can use the same rule for the negative charge, but then just flip the direction of the resultant force. So take a second to do that before you go to the next page and see what the answer is. It will take some practice to get your right hand in the right direction for these problems. But here we have a positive charge going this way and the field is coming out of the board. So I already know what to do on this one. So just bear with me. There's your hand. And you've got your thumb over there, and this is the palm of your hand, so the fingernails are on the other side. You'll want to curl your four fingers into the direction of the magnetic field, which is out of the page, and then move your thumb perpendicular. So what you're going to have, your four fingers like that, and then you're going to extend your thumb out like this, and that means the force is in the down direction on a positive charge. For a negative charge, the force is in the opposite direction. So the force on a negative charge would be up. So if we shot a positive charge in here, it will feel a force down, and a negative charge would feel a force up. And then you can remember those curves from kinematics maybe, and from dynamics. The previous slide, which showed charges being injected into a magnetic field with a certain velocity, they didn't move straight when the force hit them, did they? We kind of showed at the beginning of a curved motion. Why is that? Well, the magnetic force is always perpendicular to the charge's velocity. That means we have a center-seeking force, which results in centripetal motion. The charge moves in a circle. For example, if we insert an electron into this field, okay, and it's got an initial velocity like that, you can verify using the right-hand rule that the force is perpendicular. It's here, towards the middle. When it moves up a little bit, the force is still perpendicular, and so on. So it goes around in a circle. And by the way, if you use the right-hand rule there and you said the force goes in the other direction, that would be for a positive charge. We have to flip the sign, flip the direction for a negative charge. So in this case, we have a negative particle moving in a clockwise circle because the force is always perpendicular to the initial velocity. Where have we seen this before? Well, circular motion was covered in the mechanics section of the course. And if you look to the right, can you see a relationship between this and a gravitational force? Well, this could be a planet moving around the sun, where the planet at some time in way past history had a velocity, linear velocity like that, and then it got captured by the gravitational field of the sun, or the moon got captured by the earth, whatever two celestial bodies you want to deal with. And as long as the force was perpendicular to the velocity, you would get this motion. You would get a circular motion. Now, what happens to the speed of the planet as it orbits? See if you can remember that from the first semester. And predict what happens to the speed of a charged particle in a magnetic field. For a planet in a gravitational field, the force is always perpendicular to the motion of the planet. Just like this particle in the magnetic field, the uniform magnetic field. A difference is, for a planet, the force is in the same direction as the field. For magnetic motion here, we've got the force perpendicular to the field. See how the force here is into the picture, where if this were the Earth going around the sun, the field would be directed from the Earth to the sun. So that's kind of cool. Okay, so if the force is always perpendicular to the motion, work, which is equal to force times the displacement parallel to the motion, that's going to equal 0 because it's perpendicular. If no work is done, we use the work-energy equation. That means no kinetic energy is changed, so you keep the same speed. Speed does not change. Same is true for this charged particle in a magnetic field. Speed stays the same. In both cases, the velocity changes constantly, of course. Its direction keeps changing, but its speed is constant. And at the end of this unit, we'll see a practical use for this type of configuration. If you take a bar magnet and bend it in the middle and make a U shape, like we have here, you get a horseshoe magnet. And it gives a very nice uniform magnetic field between the poles, pointing from north to south. If we inject a positive charge with the velocity from right to left, can you show why the charge will experience a force away from the magnet? Well, let's see. You put your 4 fingers in this direction. The magnetic field is down, so when you orient your hand that way and then you pop your thumb out, it will be pointing out of the page. So the charge will be moving straight through, then it'll come out of the page. Just showing this because later we'll show how this principle can be used in motors and stereo speakers.